Introduction. Look at these things: pizza, wheel, giant wheel, coin, disc, dinner plate. All these are the examples of circle. Today we will study about circles and the properties of circles. Come, let's start. Objectives. At the end of this lesson, you will be able to define radius and center of a circle, identify interior and exterior of a circle, identify chord and diameter of a circle, explain major arc and minor arc, define circumference of the circle, differentiate between sector and segment, explain the angle subtended by a chord at a point, draw perpendicular from the center to a chord, understand equal chords and their distances from the center, explain angle subtended by an arc of a circle, explain cyclic quadrilateral. Definition. Look at this circle, and now look at this dot in a circle. This is a fixed point and is called center of a circle. We can make radius with this point. Radius is the line from the center of a circle to a point on the circle. In this figure, OP is radius. Look at this clock now. It is round in shape, or we can say that it is circular in shape. Interior and exterior of a circle. Circle divides the plane on which it lies into three parts: interior, exterior, and circular region. Let's go through them one by one. Interior. The area inside the circle is called interior of the circle. Exterior. The area outside the circle is called exterior of the circle. Circular region. The circle and its interior make up the circular region. Chord and diameter. If you take any 2 points on the circle, say P and Q, and join them, then the line segment PQ is called a chord of the circle. The chord, which passes through the center of the circle, is called a diameter of the circle. The longest chord of the circle is called diameter. Diameter is the longest chord of the circle and is equal to 2 times the radius. Here we can see that AB is a diameter. Major arc and minor arc. Look at this figure. This is an arc. An arc is a part or a portion of a circle. Or we can say that a piece of a circle between 2 points is called an arc. There are 2 types of arcs: the major arc and the minor arc. The longer one is called major arc. Here AQB is the major arc, and the shorter one is the minor arc. AB is the minor arc. The arc is denoted by this sign: circumference, sector, and segment. The circumference of a circle is the distance around the outside of the circle. It could be called the perimeter of the circle. There are 2 main slices of a circle: the pizza slice and the slice made by the chord. The pizza slice is called a sector, and the slice made by a chord is called a segment. There are 2 types of sectors: the minor sector and the major sector. Like sectors, there are 2 types of segments: the minor segment and the major segment. Now look at this circle. Here, both the arcs are equal. Therefore, these 2 are the semicircles. Angle subtended by chord at a point. Take a line segment AB and a point C on the circle with center O. Join AC and BC. Here AB is chord and angle ACB is the angle subtended by the chord AB. Also, angle AOB is angle subtended by chord AB at the center. If we draw 2 or more equal chords of a circle and measure the angles subtended by them at the center, then we will find that the angles subtended by them at the center are equal. This relation gives us the theorem which says that equal chords of a circle subtend equal angles at the center. Theorem. Let us prove this theorem. Given two equal chords PQ and RS of a circle with center O. To prove, angle POQ is equal to angle ROS. Proof. In triangles POQ and ROS, OP is equal to OR because these are the radii of a circle. OQ is equal to OS. These are also the radii of a circle. PQ is equal to RS given. Therefore, by SSS congruence rule, triangle POQ is congruent to triangle ROS. This gives angle POQ is equal to angle ROS because corresponding parts of congruent triangles are congruent. The next theorem is the converse of the above theorem. It says that if the angles subtended by the chord of a circle at the center are equal, then the chords are equal. Theorem. Let us prove the converse now. Given two equal angles, angle POQ and angle ROS of a circle with center O. To prove, PQ is equal to RS. Proof. In triangles POQ and ROS, OP is equal to OR because these are the radii of a circle. OQ is equal to OS. These are also the radii of a circle. Angle POQ is equal to angle ROS given. Therefore, by SAS congruence rule, triangle POQ is congruent to triangle ROS. This gives PQ is equal to RS. Because corresponding parts of congruent triangles are congruent. Perpendicular from the center to a chord. The next theorem says that the perpendicular from the center of a circle to a chord bisects the chord. Its converse is the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Let's prove it. Let PQ be a chord of a circle with center O, and O is joined to the midpoint M of PQ. To prove, OM is perpendicular to PQ. Proof. Join OP and OQ. In triangles OPM and OQM, OP is equal to OQ because these are the radii of the same circle. PM is equal to QM because M is the midpoint of PQ. OM is equal to OM common. Therefore, by SSS congruence rule, triangle OPM is congruent to triangle OQM. This gives angle OMP is equal to angle OMQ, which equals 90 degree because corresponding parts of congruent triangles are congruent. Theorem. If we have three non-collinear points, then the theorem says that there is one and only one circle passing through three given non-collinear points, perpendicular on the line. If we take a line PQ and a point R outside it, we know that there are infinite number of points on the line, say P1, P2, M, P3 and P4. Join these points to the point R. We can see that RM is perpendicular to PQ. Then RM is the distance of PQ from R. Or we can say that the length of the perpendicular from a point to a line is the distance of the line from the point. Equal chords and their distances from the center. Theorem. Equal chords of a circle are equidistant from the center. Let us prove this. Consider a circle of center O. It has AB and CD two chords of equal length. Now draw a perpendicular from center to AB and CD, intersecting them at L and M. So we have to prove that OL is equal to OM. Join OB and OD. We know that AB is equal to CD given. BL is equal to AB upon 2 perpendicular drawn from a center to a chord bisect the chord. Similarly, DM is equal to DC upon 2. Therefore, BL is equal to DM. Consider triangle OBL and triangle ODM. OB is equal to OD, radius of the same circle. BL is equal to DM, proved. Angle OLB is equal to angle OMD, which is equal to 90 degree, given. Therefore, by SSA congruence rule, triangle OBL is congruent to triangle ODM. This implies that OL is equal to OM by CPCT. Therefore, equal chords of a circle are equidistant from the center. The converse of this theorem says that chords equidistant from the center of a circle are equal in length. Assessment. Before proceeding further, let us know how much have you learned. Drag and drop the correct option in the blank. Results and theorems of angles subtended by an arc of a circle. The relation between the chord of the circle and the arc is that if two chords of a circle are equal, then their corresponding arcs are congruent. Conversely, if two arcs are congruent, then their corresponding chords are equal. The second result says that the congruent arcs or equal arcs of a circle subtend equal angles at the center. That means the angle subtended by a chord of a circle at its center is equal to the angle subtended by the corresponding arc at the center. Relationship between the angles subtended by an arc at the center and at a point on the circle. Draw a circle with center O. Let PAQ be an arc and be any point on the circle. If we measure the center angle POQ and an inscribed angle PBQ by the arc at remaining part of the circle, we observe that angle POQ is equal to 2 into angle PBQ. This activity gives us a theorem. Theorem. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Let's prove it. Given arc AB of a circle with center O, subtending angles angle AOB at the center and angle APB at a point P on the remaining part of the circle. To prove, angle AOB is equal to 2 angle APB. In the given condition, clearly we have three cases. Case 1, AB is a minor arc. Case 2, AB is semicircle. Case 3, AB is a major arc. Construction. Join PO and extend it to a point Q. Proof. Recall that an exterior angle of a triangle is equal to the sum of the two interior opposite angles. So we have angle QOB is equal to angle OPB plus angle PBO. 1. Considering triangle OPB, angle AOQ is equal to angle APO plus angle PAO. 2. Considering triangle APO. Also, OB is equal to OP, being radii. Angle OPB is equal to angle PBO, and OA is equal to OP, being radii. Similarly, angle APO is equal to angle PAO, thus 1 and 2 reduces to angle QOB is equal to 2 into angle OPB, 3. Angle AOQ is equal to 2 angle APO, 4. Adding 3 and 4 we get angle AOQ plus angle QOB is equal to 2 into angle APO plus angle OPB. Similarly, angle AOB is equal to 2 angle APB. Now for the case 3, reflex angle AOB is equal to 2 angle APB. Hence proved. Angle in semicircle. Theorem. Angle in a semicircle is a right angle. Let O be the center of a circle. Consider a semicircle PAQ and its inscribed angle PBQ. Therefore, 2 angle PBQ is equal to angle POQ, because we know that the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. But angle POQ is 180 degree because PQ is the diameter of the circle. 2 angle PBQ is equal to 180 degree. Therefore, angle PBQ is 90 degree. Angles in the same segment. Theorem. Angles in the same segment of a circle are equal. Given. A circle with center O and the angles angle PRQ and angle PSQ in the same segment formed by the chord PQ or arc POQ. To prove, angle PRQ is equal to angle PSQ. Construction. Join OP and OQ. Prove. As the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle, therefore we have angle POQ is equal to 2 angle PRQ. Mark it as 1. And angle POQ is equal to 2 angle PSQ. Mark it as 2. From first and second we get 2 angle PRQ is equal to 2 angle PSQ. Therefore, angle PRQ is equal to angle PSQ. Cyclic quadrilaterals. A quadrilateral is said to be a cyclic quadrilateral if there is a circle passing through all its 4 vertices. In the figure, PQRS is a cyclic quadrilateral. Theorem. The sum of either pair of opposite angles of a cyclic quadrilateral is 180 degree. Given a cyclic quadrilateral ABCD. To prove, angle BAD is equal to angle BCD, which is equal to angle ABC plus angle ADC, which equals 180 degree. Construction. Draw AC and DB. Prove. Angle ACB is equal to angle ADB and angle BAC is equal to angle BDC, because these are the angles in the same segment. Therefore, angle ACB plus angle BAC is equal to angle ADB plus angle BDC, which equals angle ADC. Adding angle ABC on both the sides, we get angle ACB plus angle BAC plus angle ABC, which is equal to angle ADC plus angle ABC. But angle ACB plus angle BAC plus angle ABC is equal to 180 degree, because the sum of the angles of a triangle is 180 degree. Therefore, angle ADC plus angle ABC is equal to 180 degree. Therefore, angle BAD plus angle BCD is equal to 360 degree minus angle ADC plus angle ABC, which is equal to 180 degree. Hence proved. Converse of this theorem is also true. That says, if a pair of opposite angles of a quadrilateral is supplementary, then the quadrilateral is cyclic. Did you know? Circles are the only one-sided shape with an area. A straight line is a circle with an infinite area. Circles have no angles. A circle has an infinite amount of lines of symmetry. Summary. Let us summarize what we have learned. A circle is the collection of all points in a plane which are equidistant from a fixed point in the plane. Equal chords of a circle subtend equal angles at the center. If the angles subtended by 2 chords of a circle at the center are equal, the chords are equal. The perpendicular from the center of a circle to a chord bisects the chord. The line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Equal chords of a circle are equidistant from the center. Chords equidistant from the center of a circle are equal. Congruent arcs of a circle subtend equal angles at the center. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Angles in the same segment of a circle are equal. Angle in a semicircle is a right angle. The sum of either pair of opposite angles of a cyclic quadrilateral is 180 degree. If sum of a pair of opposite angles of a quadrilateral is 180 degree, then the quadrilateral is cyclic.